Hi, today I'm gonna start to talk about the moment of a couple. Before I start to talk about the moment of couple, let's see what's the couple. Uh, if we have two forces, F1 or just say F, two forces that they are equal but in the opposite direction and separated with the distance d, we call these a couple. So if we have two forces that they are equal and in opposite direction and separated with the distance d, these two forces are called a couple. If you look at the one thing about these two forces is that if you look at that is the sigma f is going to be 0. So these two f will cancel each other. So there is no forces, the resultant forces as a result of these two forces, these two will cancel each other. But they have another effect that you will consider, that we need to consider. And these two effects is that these two forces may, because the resultant forces is 0, may not cause something to move in x, y, or z direction, but they will cause an object to rotate. So although they are not making something, although it may not make something to move, but it may cause it to rotate. And example for that is you can consider a steering wheel of the car. So when you get the steering wheel of the car and you want to rotate the steering wheel, you apply two forces, and each of them is the opposite of the other one. So for example, with this hand I push the steering wheel up, and with this hand down, and then the steering wheel rotate. It doesn't move, but it rotates. This is the same thing if you have a big valve and you want to open or close the valve. So you apply two forces in an opposite direction, and as a result of these two forces in the opposite direction, that valve is rotate and you can open or close that valve. So this is the result of that. So it doesn't create any it may not cause any movement because it's any motion in x, y, or z direction, because the resultant force is 0, but it causes a rotation, so that causes anything rotate. If you have it in 2D like that, and we know that there's a 2f and there's a distance d, that the moment caused by this couple is just fd. So one of them times the normal distance between them. So it's a magnitude of that moment we have. So the magnitude of one of the forces times the distance between the normal distance between two forces. If we have it in 2D, this is how we can calculate the moment of forces. And if we have it in 3D, if we want to look at it in 3D and we have the 3D, then for example, if I have them in 3D, let's say, assume I have x, y, z. So x, y, and z, and then I have two forces anywhere. So I have two forces, f, so they're equal in opposite directions. So make them. In this time, if we have a 3D, then the moment we will calculate it as before we use it in Cartesian, like any other calculation we did. So if we have a 2D, we do it in the scalar. If it's the 3D, we do it as a vector, and it's gonna be r cross f. And the r goes from one, for example, r goes from here to here. And that's how we are going to calculate that. One note that you have to pay attention is that R starts on line of action of one of the forces and can end on line of action of the other forces. So it doesn't matter at which point it starts and which point it ends, as long as it's on the line of action of the forces. So for example, I can have here, I have a R, so also I can have R like that. Also I can have R like that. So as long as it starts on one of the force and at the other forces, that's okay. The other point you have to think about that is that when I use the R, because it's a vector, which of these two vectors I'm going to use? I use this force, that for example here the top force, or I'm using the bottom, which force I'm using for my calculation. So the easy way to remember that is that if you have two forces, so again I'll draw it here, and if you have the R goes from, for example, one of them to other one, I'm going to draw it from, for example, the R from here to there. If this is the R, then this is the F. We are using it in our calculation. So if R goes toward this one, that is the one we are using for in this equation. So R go through that, this is the one we are using. It's the same if in the other way, if for example again I have 2F, and then this time R goes toward this one. So R comes toward this one, so this is the force I'm going to use in this equation. And the reason is that there's a difference between, because they are opposite and I need to use the vector, so these two are in the opposite direction, so I have to make sure I use the correct F in that equation. So in this case, if the R goes here, that is the one I'm using. In this case, this is the F I'm using it here. In this case, that is the F I'm using it in this calculation. So always remember which one R started and goes toward which force, and that's the force we use it here. So here R goes toward this top force, that's the one we are using, so the vector for that one. Here R goes toward the bottom force, so that's the one we are using it. Yeah. So remember, depend on which way you get the R, which way you define the R, then use the vector of forces that R goes toward that forces. So that's another point you have to pay attention to that. Other thing that we need to look at is the direction of that rotation. So it's which direction is going to rotate it. If we have in 2D and we want to look at that, most of the time it's easier to think of for example these two as like a steering wheel or a valve. So draw something in the between and say, assume I draw a circle in between, and look at which direction these two forces are going to rotate this circle. Assume it's for example the steering wheel. So if you look at that, you will see that this point will be moved this way. So it's gonna, this point from here start to moving toward the right, so it's gonna go this way, and this point here on the effect of that point is gonna rotate this way. So then that's gonna be our rotation direction. So it's gonna be the for example in this case clockwise rotation. That's how you can do that. In 3D format, when we want to define the direction of the M, we always use the right hand rule. So your forefinger shows the direction of the rotation, put your forefinger in the direction of rotation, and then your thumb shows the direction of the moment vector. For example, in this case, if it rotates like that, then my thumb goes toward the board, so the momentum vector created from this goes toward the board. So always use the right hand to get the rotation, the momentum direction. One other point is that in some problem you may see those forces are not sitting like that on top of each other. For example, they may be a little bit away from each other. So if I have two forces, one of them is sitting here and the other one is sitting here, so it's the F and that's the F. Still there are a couple, so still if I extend the line of action, these two forces still they are separated from each other with the distance d, and they are equal but in the opposite direction. Although they are not on top of each other, they are separated, but they are the couple. The same thing if I have, for example, a force here and a force here, and it's the F, and it's the F. Again, these two still are there are couple. Still, I can extend the line of action, and these two are considered as a couple, although they are not sitting exactly on top of each other. They have some distance from each other. One other point that I want to raise is that if you have, for example, if you have a couple like that, so I have a couple that's let's say, let's make it smaller. I have 100 Newton, and then I have 100 Newton, and they separated by 2 meters. The moment they created is 100 FD times 2, so it's going to be 200 Newton meter. The same thing here. If I again, if I assume I have two other, I have a couple. This time is the 200 Newton, and then 200 Newton, and then they're separated with distance of 1. The M they created is FT, 200 times 1, again it's going to be 200 Newton meter. And for both of them, sigma F is 0. Sigma F is 0. So for both cases, the sigma F is 0. Because of that, these two are equal. So these two are equivalent, although they're different forces, but because the resultant, whatever they're going to create, they create the same moment, the same force. So we can consider these two cases as equivalent. We can just replace one of them with another one. The other point about the moment of couple is that it's the free vector, so you can move it around and put it anywhere on the object, and when we want to do the calculation. Whenever we have the problem with moment of couple, I want to calculate moment of couple. If we do have the direct distance, if we know the normal distance, if we exactly know what is those normal distance, just use M is equal FD. If we know the normal distance, so this is the very first method, easiest method to do the calculation. If we know the normal distance, that's how we are going to do that. F is equal M is equal FD, either in 2D or 3D, so it doesn't matter. So that's how we are using that. The other way that we can do it is just calculate F, the sigma in 2D, FD. It doesn't matter which, just consider point and add all the moment for all the forces and add them together. So if you have, for example, if you have like that, for example, we have two forces here, we can do that. The other one is that, let me make it a little bit. For example, here, if I said it's the F1 and it's the, again, it's the, for example, F1. So I can say F is F1 and assume there is a point O here. So I can say F1 D1 plus F1 D2 if the distance is if the distance to that point is D1 and D2. So one point is that if you have the normal distance, use this equation. If you don't have the normal distance, calculate the moment of each of the forces respect to any point. Just F1 D1, F1 D2, so the distance for that too. Add them, calculate them, in other words, calculate the moment for all the forces and add them together. So this is the second method that we can use for our calculation to get the moment. The same thing in 3D. If you have a 3D, again, if we know if it's in 3D and if we have two forces, if we have the normal distance between them, although it's a 3D, but the magnitude again is the ft, if we know the normal distance between them. Otherwise, the other thing we can do is just go ahead and find RF. So if we don't have the normal distance between two forces in 3D, just again assume a point here, assume this is a point, and this is going to, for example, be R1, and this is going to be R2, and then calculate the moment for each of forces about that force, each of forces about that force, and add them together. Or the third method is just, if you have RF, which is, if for example, if we know if this is the R, so R going from one of them to other one, so we can calculate the position vector between one of them, and to other ones. So in simple word, if you have the normal distance between two forces, always use this equation. It's the easiest one. So you can calculate the momentum Ft. If you don't have the normal distance, it's not easy to do that. You can just calculate the moment of each forces respect to any given, respect to any point. So calculate, for example, moment of all forces respect to point O, and then add them all together. In 3D, the same thing. If you have the normal distance between two forces, just use this equation. If we don't have the normal distance between two equations, we can come and calculate the moment of each forces, again, respect to a given point, and add them all together. For example, here we calculate the moment of F respect to O, calculate the moment of this F respect to O, and then add them all together. Or we can find like that, if there's a, we know the position vector goes from one force to other force, then we can use this equation to calculate the moment. So there's a couple of methods. We can use it in 2D or 3D to calculate the moment of couples. Okay, let's look at an example. If we have then object that we have a couple of forces here, a couple of forces here. So we have two couples. Apply on that, and we want to calculate the moment, the resultant moment in this figure. See how we can do that. So the very first method is that I said, if we have the normal distance between two couples, we can use that for the calculation. So here, the first method is that I'm starting, for example, assuming, first of all, I assume the counterclockwise rotation is positive, and the resultant R is. So I start from here, calculate the very first ones. So assume I start from these two. So if we look at these two, so the moment they are creating is the Ft, so the F is 10, and D is the normal distance between these two, which is given is equal to. The direction is going to rotate that, is going to rotate it like that. So if you assume you draw a circle between that and see which direction these two forces are going to draw that, rotate that circle, is going to rotate it like that. So it's going to be clockwise. We assume the counterclockwise is positive, so because it rotates clockwise, it's going to be negative. Then we start to look at these two couples here, these two. So these two couples, so these two are also a couple that are equal and the opposite direction. So their magnitude is Ft, so it's the 20, the F, and the normal distance between them is 1.5. And the direction is going to rotate, again, if I draw the circle between these two, it's going to rotate it like that. It's going to rotate it counterclockwise. So it's going to be plus, because we assume counterclockwise rotation is plus. So if we calculate this, it's going to give us 10 Newton meter, and because it's positive means that it's going to rotate this object counterclockwise. So it's the first method because we have the normal distance between two of them. So we first we use this couple, moment of this couple, and this second we calculate the moment of that couple. But also remember I said we can't use, if we assume we don't know the normal distance, still we can calculate the moment by just adding all the adding all the moment created by all the forces. So I'm assuming here I'm going to calculate all the forces about a given point. So here I start to calculate everything about point O. So to do that, again, I assume the counterclockwise is positive, so MR is, I start from top here. So this force goes through the point O. It goes through the point O, so it doesn't create any moment. So it's going to be 20 times 0. So that's one is just 0. It goes through the one. This one is rotate respect to point O, want to rotate this object counterclockwise. So it's going to be positive, and the magnitude is 20, and the distance, the normal distance between the force and point O is 1.5. 1.5. Then I come to this force here. Again, if you look at that force, respect to point O, it wants to rotate the object clockwise. So it's going to be negative because it's rotated clockwise. And it's going to be 10, and the normal distance between the 10 and the point O, the normal distance from this and point O is 3. So it's times 3. And then this force, it want to rotate counterclockwise. It want to rotate the object counterclockwise respect to point O. So it's going to be positive, and F is 10, and the normal distance between here and the point O, so the total distance is 3, this one is 2, so this distance is going to be 1. So normal distance from this to point O is 1, so it's going to be 1. And we do the calculation, this one is going to be again 10 Newton meter. So you see we can use the couple equation to calculate the moment. So there's two couples, we just add them together. Or we can just go ahead and calculate each force is one by one about given point, and then add them all together. It's going to give you the same result, depend on the problem and how the distance are given. So it might be easier to do it this way, it might be easier to do it this way, but it's going to give you the same result. Okay, now let's look at the how to calculate the moment of a couple in 3D. Here, assume we have an object in 3D that it has this shape and has a F1 and F2 apply on that object. So we want to calculate the resultant moment on this object. So if I come here and says, okay, this is my point O, this is point A, and this is point B, and I do the calculation. So first of all, let's get the coordinate of these points that I have. So I know that for point O is just 0, 0, 0. For point A that I have, for point A the X is 2, the Y is 3, and the Z is also 3. So it's a 2, 3, and 3. And for point B is also going to be, the X is 2 again, the Y is 4, so it's a 2, the Y is 4, and the Z is also 3, similar to A. So these are the forces I have to do the calculation. So I start to do the calculation. So very first method that we were talking about, if we have the normal distance between the two forces, we can just calculate that, say, okay, M is equal FD. That's the very first method that we can use. So I'm going to put it here. So the first method, the magnitude is FD in 3D. So one of the forces is 100 and the distance between them is 1. And which direction is going to rotate? So it's going to be one. It's going to rotate it like that. So if I look at it, it's look at like that. So it's going to be 100 Newton meter. And if I want to get the vector for that, it is the unit vector times it's the magnitude times the unit vector. So it's magnitude times the unit vector. So its magnitude is 100, and the unit vector, look at that, how it's going to rotate it. So sorry, this one should be upward, so it's going up. So if you look at that, how this F1 F2 is going to rotate us, so it's going to rotate the object like that, and so my finger is going to be toward the outside the board or toward the X, so it's going to rotate like that outward. So the rotation, the vector of the moment is going to be outside the board along the positive X. So what's the unit vector along the X? Is just I. So the unit vector along the X is I. So it's going to be 100 I. So that's the simplest way of doing it. If we know the normal distance, that's how we can do that. The second method is that go ahead and calculate the second method, calculate the moments. Go ahead and calculate the moment of each of these forces respect to given point and then add them all together. So I'm going to second method, how to calculate the M. It's just I go ahead, I calculate the moment of F1 respect to O, F2 respect to O, add them together. So that's the first method. The second method, is I'm going to say that the M is F1 R1 plus F2 R2. I just add them together. So I calculate, in other words, it's just sigma FR. So I calculate the moment of each force's respect to given point, and then I do the calculation. So in this case, I can say that the M is F1, and the R1, the position vector here, the position vector I'm gonna have is going from, the position vector would be for the F1 is this one. So that's the position vector going from O to A. So for the first one. And remember, the position vector can go to anywhere on the line of action, so it doesn't matter where. And for the point B, this is the position vector I'm gonna have. So this is gonna OB. So for the F1, I'm gonna calculate, so it's the ROA, plus for the second one, it's gonna be F2 times ROB. So the position vector for OA, calculate the position vector for OA. So R for OA is XA XO I plus YA minus YO J plus ZA minus ZO K. So these are the three vectors have. So ROA it's going to be 2I plus 3J plus 3K. The same thing for ROB. So I have ROB is again XB minus XA I plus YB minus YO. Oh, sorry, that's a O minus YOJ plus ZB minus ZOK. So if I just plug in those value. X minus xb minus is going to be 2i plus 4j plus 3k. So it's the ROV and the ROB. So these are how I can get. So if I substitute them into these two, one, and then I need the F1 and F2. So the F1, again, look at the F1. Remember, anytime that we have a force is parallel to one of the axes, the unit vector is just, we are using the unit vector for axis, and the direction shows is positive or negative. For example, here for the F1, it is parallel to the z-axis in a negative direction. So the F1 is its magnitude 100. It is negative because it's going against the z-axis, the opposite direction of z-axis, and the unit vector for z-axis is just k. So it's going to be minus 100k. The same thing for F2. It's going to be positive. So if you look at the F2, is going to be positive. It's parallel to z, and the positive. So the positive is magnitude, and because it is parallel to the z-axis, so it's going to be the k. The same thing if it was in the positive direction of x, it would be 1. For example, if it was 100 and parallel to the positive of x, it would be 100i. It was in the opposite direction of x, parallel to x, but in the opposite direction it was 100i. So just the magnitude plus or minus that shows is it positive or negative direction of that axis and the unit vector of that axis. Here is parallel to the z, so we can just write it and very simply write that. So now we have these four. So we have ROA, we have ROV. So these four that we can substitute in this equation to get the value we want. So I just write them down here, so I can just write them very quick down here so we can use it. So ROA is 2i plus 3j plus 3k. ROV is 2i plus 4j plus 3k, and F1 is minus negative 100k, and F2 is 100k. So I'm gonna just substitute up there. So again, I said that F is F1 cross ROA plus F2 cross ROB, and then if we put them these two together, so we have them, we talk about that. So it's a cross vector, we can use it as a determinant. So it's going to be the first determinant for this one is going to be I, J, K, and it's going to be 2, 3, 3. So it's a 2, 3, 3. So it's a Rx, Ry, Rz, and then the value of the sorry, I wrote them in the wrong way, so let me write. So it's a ROA times F1 plus ROB cross F2. So 2, 3, so these are the component of R, and then the component of F1, which is going to be 0, 0, and negative 100, plus the determinant for this one. So this determinant is going to be again I, J, K, and then we have the component of R, OB, so it's going to be 2, 4, and 3, and the component of F2, which is 100K, so it's a 0, 0, and 100. So again, if I want to say that this part is going to be this determinant, and then this part is the second determinant. So this is this determinant, and this is this determinant. So if we we calculate the third determinant, and for this one, if we calculate the determinant, so for the first determinant, what we are going to have is the first determinant is going to be, if I said consider the first one, remove the first column and first row. So it's going to be I, remove the first column row, so that I is there. So it's going to be these two minus these two. So these times this minus this. So it's the 3 times minus 100 minus 3 times 0. And then I. Then I go to the second one. Remember, the second one is negative, and then I remove the column and the row that the J is sitting in there, and then they do the calculation. So the 2 times negative 100 minus 3 times 0 J, and then the third one is plus. Again, so I use the K, I remove the row and the column that the K is in there. So it's the 2 times 0 minus 3 times 0 is the 2 times 0 minus 3 times 0 K. So this is the first determinant. So this is the second determinant here, again, plus. So I start with the I remove the row and the column that I is in there and calculate the rest. So it's a 4 times 100 minus 3 times 0. So it's a 4 times 100 minus 3 times 0, I. The second one is negative. I go for the J. I remove the row and the column that J is in there. I calculate the rest. So it's a 2 times 100 minus 3 times. So it's 2 times 100 minus 3 times 0 J, and then this third column, which is going to the third one, which is going to be K, remove the row and the column K is involved and calculate the determinant for the rest. So it's a 2 times 0 minus 4 times 0. So it's going to be 2 times 0 minus 4 times 0, and then the K. Again, the same thing here. This is the first determinant. So this is the first determinant, and this is the second determinant. So we just add these two together. We'll simply add them together, and if we add them all together, we will end up having, and this is, remember, this is vector. So we are going to have M is going to be 100 I. So if we add all these components together, eventually this is what we are going to get. So it's the same result, if you remember. So in the first method, it says that we can just use if we know the normal distance between them, it's just times FD. So it was 100 times the normal distance between these one, so it was 100. And the second method also gives you the same thing. So in the first method, we just said that because we know the normal distance, just FD, calculate FD, and that's the moment you get. In the second method, calculate the moment of each of the forces with respect to given point and add them all together, and it will give you the same answer. The third method is that you go ahead and do the calculation for the couple in 3D. So assume you have a couple in 3D. So it's going to do for the third method. third method is that I'm going to say that, okay, M is just R times F, the 3D format of the couple. And what's going to be R? This is going to be, so R is going from one of them to the other one. So assume that the R, I'm consider this is the R, go from A to B. So that's the R I want to have. So it's going to be, in here it's going to be, in other words, it's going to be R AB, because I chose R AB. And because it goes toward B, that one's going to be F2, because R goes toward F2, so it's going to be, the R is going to be RAB, and because it goes toward F2, that's F2 I'm going to use in my calculation. So I need the RAB, which is XB minus XA I plus YB minus YA J plus ZB minus ZA K. So if I use these A and B coordinate here for RAB, so I'm gonna get for the B minus A. So B minus A is gonna be 0I plus B minus K is gonna be 1J plus 0K. So this is going to be my RAB. And the F2, we know that here we have it, the F2 is 100K. And then if we calculate that, so M is RAB times F2. It's going to be, again, I, J, K. Then the component of the R, which is going to be 0, 1, 0. And then the component of the F is going to be 0, 0, 100. And if I calculate these determinants, so it's going to be I. So for the first one, I remove the first row and first column. So it's going to be 1 times 100. 1 times 100 minus 0 times 0. It's going to be 1 times 100 minus 0 times 0, and then times it by I. And then I remove the row and column that includes J, so I remove these two. And remember, the second one is always negative, so it's going to be 0 times 100 minus 0 times 0, and it's going to be J, it's times J. And the third one, so we remove the row and column that it has K in it, and then we have 0 times 100, 0 times 100, 0 times minus 0 times 0, minus 0 times 0, and K, which if you look at that, this is 0, this is 0, and this is 100, so it's going to be, the M is going to be 100 I. So it's the same answer as the previous two methods we had. So again, I said if you have dealing with the 3D and want to calculate the moment, the very first method, that's probably the easiest method, is that if you have the normal distance between the two forces, just calculate FD. The D is the normal distance between two forces to get the moment. If you don't have the normal distance, the second method you can use that is just go ahead and calculate the moment for each of the given forces respect to the given point, so to one point, and then add them all together. And the third method is just that use the 3D calculation for the moment of a couple like that, and calculate and find the moment. All three methods gives you the same answer, and you can use either of the method, depend on which one would be easiest for the problem you are solving.